Hi, so this is Organic Chemistry 2. It's the second test, and we've already kind of done a practice test video last semester on the stuff that's going to be on this test. So this is just kind of an open office hours where we're going to talk about different things that might show up on the test, different questions, different clarifying ideas. The first question I just got was about what are some conceptual things that might be asked about this test? And I think that's a really great question. So this test, if we zoom out, what were the main topics that we talked about this test? Um, that's kind of hard to describe because there's a lot of organic chemistry too. So essentially, the main point of this test was carbonyls, right? So that was the heart of it, carbon eels. That was the heart of what we were doing, and we kind of explored all the different kinds of additions. So what happens if you add an alcohol into a carbonyl? What happens if you change the kind of carbonyl it is, right? So you guys might have noticed by now, if you zoom out, adding, say, an alcohol into a ketone is going to give you a completely different kind of reaction than adding an alcohol into, say, an ester or an acyl chloride, right? So the heart of the class is carbon. The heart of this unit is carbonyls. So you get all sorts of reactions. We can kind of summarize it, but uh, the large summary is that you follow the reaction mechanisms and you see what you get, right? But when we zoom out, when we have some sort of heteroatom here, we're going to be doing some sort of substitution, right? Where Y is a nucleophile. That's a big idea. And then when this is C or H, we're usually getting some sort of we're usually getting some sort of addition. Um, or you know, some sort of addition, and then we can eliminate the alcohol. So depending on what Y is, we'll keep going in this reaction scheme, but there's not necessarily a leaving group to substitute out. So this is kind of the heart of the unit. I would say there's not a ton of conceptual things I'd worry about. I'd be pretty good with the mechanisms. I guess the big conceptual thing with this would be equilibrium, and this kind of lies with everything. Understanding why we might say take a carbonyl, a ketone, and when we add an alcohol to it, you notice that you get after you follow tetrahedral intermediate, you do all that stuff, right? Recognizing that in this equilibrium, we're really not going to favor that product very much at all. So in order to bypass that, in order to add this alcohol into this carbonyl, if that's what we wanted to do, um, we need to add excess, right? Le Chatelier's principle. So that's why we tend to get acetals when we add into these kind of carbonyls, right? So understanding equilibrium when it comes to these carbonyls, that would be a good place to think about as a potential place that I could ask a conceptual question. So being able to explain different equilibrium concepts where, you know, something like this, if I add a nitrogen and I get this, well, that equilibrium is still going to favor the forward direction, right? Nitrogen's a better nucleophile. We can get that addition into that imine, and it's not a big deal, right? So this equilibrium would favor this product, where it would favor this product with an alcohol, right? So understanding the difference between a nitrogen and an oxygen in terms of how good they are as leaving groups, how good they are as nucleophiles, that's kind of the heart of the conceptual stuff. And then everything else is just mechanisms and products. So that would be the deal with carbonyls. More specifically, another conceptual thing is carboxylic acids are a little tricky. I saw a question in the chat. Feel free to hop in and just ask a question. Um, it's gonna be a little bit slower to answer on chat, but I'd be happy to check it occasionally. Okay, so before I move on to carboxylic acid, someone said, um, how do I determine stability? And yeah, that has to do with, right, of equilibrium. So let me move this. So at this point, I'd be comparing that water to that amine in terms of nucleophilicity, right? So this is more reactive, so we're going to get more of this product, right? Nitrogen's a better electron donor, it's a better nucleophile than an oxygen. So all things being equal, we're going to favor this side. But I mean, if you compare that to this, we're essentially it's water compared to this alcohol. There's very little difference between these two things, right? These two things are both relatively stable. One's not like a significantly better electron donor than the other. But the big difference comes with this product is positively charged. There's not really a great way to get rid of it. So this side of the equilibrium would be favored. So there's no one size fits all, but you kind of look at what's the least stable thing in the picture, right? So to me, that nucleophile is ready to go. It's ready to react. That's the least stable thing in this whole picture. So I'm going to favor the other side. To me, that's the least stable thing in this picture. It's got a charge. I'm going to favor this other side. So understanding that in equilibrium, I think helps point. So someone asks, this is a good question. Why don't we form like an enamine-like thing? So essentially get to this. The reality is we could. That's definitely possible. But it would just be a very slow reaction because this equilibrium does not favor this side at all. So in reality, you're forming very little of this side ever to begin with, right? Um, like this doesn't want to turn into that very much. So relying on getting enough of this to start eliminating it is kind of a hard question. Like you're not going to get a lot of that to happen. Whereas with the nitrogen, nitrogen's okay picking up that positive charge, and even to the point where like if this was like dimethylamine or something, some like if we were here and this is positively charged, it still might favor this side of the equilibrium. Like nitrogen's okay taking a positive charge, like we will form plenty of this to do the enamine formation. Whereas in this equilibrium, we're forming so little of this that to get this elimination to happen is very unlikely. It'd just be really slow. It's possible, but you'd be better. People just add excess and get here if that's what they are trying to do. Forming that product would be hard. Someone said, "Hi, will everything in today's lecture be fair game for the exam?" Everything up into those last couple questions that were kind of review difficult questions. But yes, I would expect you to be able to do basic protecting groups on the exam. So being able to recognize, oh, I need to protect this alcohol and just put PG, right, as the protecting group, would be something that would be a fair game exam question, just like protecting a acetal. So, yes, protecting groups as a part of synthesis will be on the exam. You'll have to protect something. If you forget to protect something or don't protect something, you can still probably do the synthesis and just lose a point or two, right? It would be like, oh, this needs to be protected, and you just move on with your life, right? But for a perfect score, protecting groups would be on there. As it stands, they're bigger fish to fry. Like if you're struggling with other things or you can't do a good mechanism or you're losing points on quizzes that you don't understand, those are bigger fish to fry than today's lecture. But today's lecture, if you're aiming for a perfect score, would be good to look over. All right. Are there going to be questions asking the starting and ending functional groups in the exam, like at the end of the recent lectures? Um, so hold on. Before I answer that question, let's finish talking about some conceptual things I might ask. So equilibrium, I think, is a big one. That might be the biggest confusion, just being able to understand, hey, what's the least stable thing in this picture? In this case, it's that nitrogen wants to wants to be, remember I compared a nitrogen to a dog that doesn't know when to stop eating, right? Nitrogens love having positive charges. They love giving their electrons away. So usually I'm looking at stability of charge, I'm looking at quality of nucleophile, right? All those things. One thing that could be asked with carboxylic acids is to explain like, right, the heart of carboxylic acids is that in acidic conditions, that is an electrophile where that is a nucleophile in basic conditions. So some questions that could come up with that are, you know, you've done them at this point, right? Why, like, what acid do I need an acid or a base in this situation, depending on what I pair it with? Do I need, if I have an acid or a base, do I need to pair it with a nucleophile electrophile? What's going to be on that nucleophile electrophile? Um, Being able to explain like acid strength, right? Like why can I use a weak base? Because carboxylic acid is a strong acid. Why is carboxylic acid, if I deprotonate it, it is a nucleophile, but it's still kind of a poor nucleophile. That charge is delocalized, right? So there's resonance here. So understanding that there's resonance that might lead to it being a weaker nucleophile or not as good at attacking things as other things, but it is still nucleophilic. Um, Kind of a similar thing with epoxides, being able to explain, hey, in acidic and basic conditions, what do I get and why, right? Like in acidic conditions, this forms what we call the thermodynamic product. So this is the more stable intermediate. In acidic reactions, we don't have a negative nucleophile sitting around generally. So um, you care about stability, where basic is faster, right? So in basic conditions, we have a negative nucleophile. And so we care about speed. It's going to attack the more accessible carbon. So carboxylic acids, epoxides, those are kind of those are good. I would say this is kind of the heart of the conceptual questions for this exam, right? Everything's going to fall into this. Either we're going to ask about equilibrium, we're going to ask about why different reactivities happen. So I kind of consider these to be parts of mechanisms, right? If you really understand mechanisms, you can kind of extrapolate why things might happen, right? If you understand that negative charges want to go now, it explains why epoxides do what they do. If you understand nucleophile and electrophile, how those things pair with acids and bases in general, right? We've known from the beginning that acids activate nucleophiles or activate electrophiles. So how does that work? What is the electrophilic atom? How do we fill in the blank from there? And then equilibrium is its own thing that kind of plays into the reactivity of everything with carbonyls. Well, it kind of plays in the reactivity of almost everything. Um, SN1, SN2, E1, E2 is just equilibrium zoomed out. So yeah. Someone asked, all right, are there going to be questions asking for the starting and ending functional groups for the exam? I would be prepared to do that. I'd be prepared to name functional groups specifically. I care mostly about the functional groups, the kind of the newer functional groups, right? I care that you know what an acetal is, what an imine is, what an enamine is, what a hemiacetal is. The ones that we made this unit, right? Like I would be able to name an imine. I'd be able to name an enamine. I'd be able to name an acetal. To be honest with you, when I see MCAT stuff, a lot of it is they'll name just either it's like Orgo 1 stuff that's like, oh, you know, what's this Newman projection or something, or it's uh, an Orgo 2 reaction where they just start throwing functional groups at you. And so being able to recognize, I've seen MCAT questions that use the word enamine. They say, hey, this enamine acts as a nucleophile. So what kind of electrophile would you need? And so being able to use that terminology and recognize that terminology is important to be able to succeed at the kind of questions that MCATs ask. So I'm going to make sure that you're very functional with very familiar with functional groups. Um, is there going to be any material from exam one like spectroscopy? There's a lot of material from exam one. Notice you've been doing tetrahedral intermediates pretty much this whole chapter. That was on exam one, but in terms of there will not be a spectroscopy question on exam one. Um, Someone said, will there be a question on which side is favored or if it's in equilibrium? If so, how do we determine that? Yeah, we've already talked about that a little bit. So equilibrium is a fair game question. Um, and really it comes down to being able to assess relative strengths of leaving groups or nucleophiles. Oftentimes you're best off looking at the most stable charge um, in a system. So that's usually a good place to go. Another place to look if everything's neutral is to say, hey, one thing's a better nucleophile than the other thing, so I'm going to favor the other direction, right? One thing's a less stable set of electrons, less stable charge, so I'm going to favor the other side. I'm going to favor the more stable side. Um, you can go back and look through old practice problems from the lecture notes where we talked about equilibrium, but in general, what you're doing is you're looking either at the most stable charge or if everything's neutral, favoring the side away from the better nucleophile. When should we assume there is H2O or H3O to quench reactions? Is it only assumed under acidic conditions? Uh, so, no, it's actually kind of the opposite. So, okay, yes, okay, sorry. So let's talk about that real quick. So if I acidic conditions imply water. So oftentimes at the end of an acidic reaction, you end up with some product like this that's got a positive charge, and we can imply water, right? Most acids come in water. So if you buy like HCl or sulfuric acid or whatever, it's going to be in an aqueous solution, right? Like it's X%, 1 molar sulfuric acid in water or something like that. Um, so there's water around, and that will often quench the end. Um, Basic conditions are done free of water. So that's here's another good potential conceptual question, right? We talked a lot about like a Grignard is a prototypical basic reaction, right? So if I want my Grignard to add into a carbonyl, I wouldn't want water sitting around because it will add into that water first, which is not good. So if there's not water sitting around, what ends up happening is that I end up with a negatively charged thing, right? Because this thing will chew up any free proton sitting around, it'll chew up any acid or any water sitting around. We don't want any water or acid present. So in these, we have to add some sort of acid or some sort of water to protonate this at the end. So it's less that like, can we imply water with acidic conditions? Sure. It's more that in basic conditions, we're water free. We have no water. We ensure that there is no water. And so in order to make the reaction neutral at the end, we have to add water more than it's, I think I think this is the better way to think about it, is that basic conditions are free of any sort of acid or water because it usually would interact negatively with the base. The base would attack the water instead of the other way around. Oh,
Wait, so can I ask one question about that?
what's up?
If we were to, let's say at the end of a basic reaction, we were to have like some sort of charge on the product to deprotonate that product, we could add H2O at the end.
Yeah, and
Or
water in acidic conditions, water is going to be around. That's safe.
um
And I don't care if you deprotonate with the conjugate acid or conjugate base of whatever acid you use, like the Cl off of HCl or water. We just need to get it deprotonated.
but is there a case like when you're doing basic conditions, I can't remember off the top of my head right now, where you're gonna end with a charge? Like not in acidic.
Yeah, in basic conditions, you're almost always going to end with a negative charge because you have a base in there that's soaking up any sort of protons.
Would you
So
protonate that?
in basic conditions, we have to add like a proton source at the end. That's why
Okay.
oftentimes with basic conditions, you'll see we write it like this. What that's saying is we're doing this whole reaction between the Grignard and one, and then at the end, when I get that negatively charged thing, I'm going to add the water
Okay.
or the
Thank
acidic
you.
or the acid, right? So this is saying that this happens at a completely different step because we want to make sure it's neutral. Whereas we don't need to do that with acidic conditions because there's water around. It's going to kind of neutralize whatever we got.
Got it. Thank you.
Um, so someone asked about retrosynthesis. Just going over retrosynthesis, is there a way you would approach any synthesis problem? Personally, I have a hard time seeing when the starting material was epoxide and built from there. Okay, so we can talk about synthesis for a second. So at this point, you guys have a couple of reactions you know. So if the heteroatom is part of the reaction or part of the squiggle, like part of the new bond you form, then it's going to be a substitution reaction. If you have, I'm just going to do it. We don't need this. If the heteroatom is one away from the squiggle, then it's going to be a Grignard. All right. So the important thing is we got to find the squiggle based off the carbons we have in our starting material and then work backwards from there. If that heteroatom is two carbons away from the squiggle, then we'll have to use an epoxide. So that's the heart of it. That's we do retrosynthesis over and over and over again because being able to recognize this just helps so much, right? If you know how to make the squiggle and you count two carbons away, your OH, or it doesn't even have to be OH. I think it'd be better if I just said whatever heteroatom Y is here is two away from wherever that squiggle has to be. It's got to be an epoxide. Period. End of story. So when I do a retrosynthesis, I make the squiggle, I see two carbons away, I think, well, that's got to be an epoxide. So Ivan, do you have questions about that more? What are you missing as part of that? Is it just the concept of like doing a squiggle? Is it understanding like seeing the heteroatom two away? Where are you missing the epoxide?
I mean, like personally, like it's I don't think I have like a problem other than like with the epoxides and like the newer stuff like um the nitrogen adding and stuff like that, protecting the nucleophile, protecting the carbonyl groups,
Okay.
but it's just like newer stuff.
Okay. Yeah, the nitrogen's a little different, right? So I've got a nitrogen. I have to do the reductive amination. So instead of a leaving group, I should have done this other way. Right, instead of a leaving group here like we had with the alcohol, nitrogen's just a little bit different. We've got to do a carbonyl here. And that actually, that doesn't form that directly. It forms this. Forms an imine, which we can then reduce. So, yeah, nitrogen's a little bit different. The acyl chloride one, I think, is pretty straightforward. So if you've got this, so really these are all the major bond forming reactions. These are anything that you could potentially do in a retrosynthesis. It kind of all goes back to these, I guess, 5 reactions at this point. And even then, like, I'm not that convinced that this reaction is significantly different than this one, right? You can kind of see a lot of the similarities. It's an alcohol with a thing with a leaving group. Um, and this one, which is just an alcohol with a thing with a leaving group on it. The protecting group just is a different thing entirely. It's more like you do your retrosynthesis and you look at it critically for a second and you say, is there another nucleophile or electrophile um, that could possibly interact with this? That could be a problem. And so if you see that, if you see, hey, there's 2 electrophiles here, I need to figure out how to protect one of them. Or hey, uh, there's 2 nucleophiles in here, I need to protect one of them. So knowing how to do that. So protecting groups for carbonyls, I would want to use some sort of thing, use some sort of diol with an acid, H2SO4 works. That would protect a carbonyl, and then both OH and NH. You can just write PG. That's fine with me. So someone's asking about the example, so we'll do this exact example. An example of this, right? What's actually going on here? The mechanism. So let's talk about the mechanism. Usually some sort of acid. So electrophile takes proton. Nucleophile attack electrophile. Great question, by the way. If there's ever anything you don't understand about what we're doing in synthesis, we're not doing a single thing in synthesis, really, especially these major bond forming reactions that you haven't done the mechanism of 100 times. I formed a tetrahedral intermediate, so I'm going to save time because don't do this on the test, but I'm going to transfer the proton over to the other side so we don't have to do it. But I'm just kind of for showing mechanism of something. collapse and kick, and you're left with an imine. So that's what's happening there. You're essentially kicking off this carbonyl as water, and you're doing this imine formation. It's gonna have a positive charge. You deprotonate it. That's the end of it. Um, so on that same note, this is the main difference between an imine and an enamine. So, all right, let's say I'm going to draw this just slightly different. Let's say I do this reaction with some sort of acid. I'm going to get this, the same mechanism we just did above. I mean, deprotonating it would not get you to the product. It would get you to the imine. So if I wanted to get to this, I would have to then reduce it. That would be a different step. But yes. So that's an imine, totally fine, right? So if I change something about this, and I try to draw that same imine out, I have a positively charged nitrogen. I have a nitrogen with 4 bonds on it, and there's nothing I can do about it, right? There's no hydrogen I can take off. So an imine forms because you can't neutralize the imine. Sorry, an enamine forms because you can't neutralize the imine. And that happens with secondary amines. Because there's only 1 proton to remove, not 2, right? Or you can think about it as a nitrogen only wants 3 bonds, and when you form the imine, this nitrogen's gonna have to be positive. It's gonna have to have a 4th bond. So that's when we form the enamine, because we literally could not have an imine without it having a positive charge we couldn't get rid of. So this is imines, enamines. Here's the mechanism of an imine formation. Does that make sense?
For the mechanism that you did up there, how would you get that final product like before you, how do I explain this? Before you made it the imine, how would you get the original product you were trying to get from that, like the one with the positive charge?
What do you mean?
Okay, like um the original retrosynthesis problem you were doing, like right there, how would you get from that mechanism that you're doing below it, like the end product to that final product up there?
From here to here?
Like with the positive charge on the bottom right.
Well, it deprotonated, right? The product is this.
But then it like doesn't have the H on it.
Yeah, it shouldn't to be neutral. Right, so this is the product of the reaction between these.
Oh, okay, yeah. So then how do you go from that to the NH one?
Well, what's the difference between the two?
That it has an H?
Where?
In
Here?
the, yeah.
Well, sure, but that's small cookies.
So we don't have to show us going from the imine to that.
No, I mean you do. There's a much bigger difference than just a hydrogen, right? Well, you actually added 2 hydrogen. That double bond didn't just disappear. What happened?
Like, would you use a reagent to get it from that to that? I'm just
That's
a
what
little
I'm
bit
asking you.
confused,
What's
honestly.
changed?
The age.
What?
The age, right?
Well, I mean, if I just put an H on this, that doesn't exactly look like the final product, right? Something else
Yeah.
has changed. What is that? What else has changed?
The double bonds.
Okay. Well, double bond's not a thing. Mendeleev didn't even believe electrons existed, and he made the whole periodic table. What's changed? You've got yourself into this trap.
I'm a little bit confused.
Okay, yes. Clearly, this gained a proton, but that doesn't solve all the differences. What else has changed?
Like the fact that there's a not a double bond on the N anymore,
Okay. Is that it?
and that there's an H on the N.
Okay, so I can just move this here.
Right.
I can move that there, and would that get us the product?
Yeah.
No, it would not, actually. We'd get that. Right? I mean, this carbon would lose a bond, right?
hmm
Would have a positive charge. So that doesn't get us there either. You're missing something very important. How many hydrogens are on this carbon?
One,
How many hydrogens are on this carbon?
two.
Where did that hydrogen come from? Is this a nucleophilic or electrophilic carbon? Yes.
Electrophilic
Why?
because it has um the double bond on it.
Right, it looks kind of like a carbonyl, doesn't it?
Yeah.
All right, let me ask you a different question.
hmm
What's the difference between these two things?
One's an alcohol and one's a ketone.
Okay, so what's the difference?
The H, like the H and the double bond.
Okay, well, how do I get from one to the other? How do I do this reaction?
The reducing agent,
Like what?
like LAH,
Sure. What does LAH do?
it reduces the like the ketone
How?
by the H attacking the electrophilic carbon.
Right? We gotta explain that hydrogen. Yes?
Right. And then
So how do I go from here to here?
with a reducing agent.
Yes.
And then you said that we could use NaBH4 or L. Yeah, sorry.
Yeah.
Actually, literally just writing that out.
Yep. So we need a reducing agent here because what's important is that we're adding a hydrogen to this carbon. And we need a
Right.
nucleophilic hydrogen to do that. Right? So just protonating this isn't the same.
Did you want us to know this mechanism?
Mechanism of getting from here to here?
Yeah.
Oh, you should be able to do it.
Okay.
It's the same mechanism as here. I mean,
Yeah, that's true.
there, I've learned the mechanism.
No,
Right?
thank you.
Yeah.
Took us a little minute, but
Yeah. I mean, just think about this being a carbonyl, right?
right.
I want to get the carbonyl to an I want to get a carbonyl to an alcohol, I have to add a reducing agent. If I want to get this, which looks a whole lot like a carbonyl to an amine, I have to add a reducing agent. It's the same thing, it's the same mechanism. We've just replaced a nitrogen with an oxygen, but everything else is the same.
Okay. Is that in like a separate step, the reducing agent?
Yeah. You can do one and two with the reducing agent. That's very commonly done.
Okay.
So how
Like
that would
one
look
is
would
the ketone and then two is the reducing agent.
so how that look would be like, yeah, these are good questions. So one would be a ketone with some acid. So, and then two would be some sort of reducing agent. NABH4 is more commonly used, so
And then the acid should be there, right? For the to make the ketone a better electrophile.
yes.
Okay.
So I don't know if you guys picked up on this, but the rule of thumb is essentially like if we're adding into a carbonyl, I usually add an acid. If we're adding into if we're doing a substitution reaction, I add a base. So if the electrophile is a carbonyl, so electrophile, it's usually acid catalyzed. This kind of goes back to someone's question earlier. But if my electrophile is some sort of leaving group, because like halogens aren't going to ever want to be positively charged, right? Like we're not going to go, right? Like a halogen, like a bromine wouldn't want to ever be positively charged. So we usually use base. So any sort of carbonyl, look, I mean, acid catalyzed, acid catalyzed, acid catalyzed. So of all of the reactions up here, I would say this is acid catalyzed, right? This isn't, this can't be acid catalyzed because we're in basic conditions, right? So I don't need an acid here. Uh,
Sorry, before we move on from um the nitrogen group stuff, so for that synthesis, you did an example in the third class and stuff, and it was how like you didn't when you did it separate, you had going from the amine, it has NABH4, and then to the second step is H3O plus. And but then when you did it like S1, you just have the one step is the amine with the acid and then the NABH4. Are we gonna need that H3O plus or H2O? Or no? Like is
yeah, I mean, if I wanted to be super technically correct, this would be H3O plus here.
it okay? So if we just do one the materials without the H2O plus, would we get full points for that? Like two.
Yeah, like when we're in synthesis mode, I'm less worried about like quenching steps.
Okay.
Like if you show the Grignard and forget H3O plus, I'm not too worried about it. Um, that doesn't mean that you should ignore all acid and base.
Right.
Uh, it's kind of a hard thing to describe, but yeah. If I were you, I would just include it. Recognize essentially if it's acidic, I don't need a quencher, but I need to add an acid. If it's basic, like sodium borohydride is a base. It's a electron donor, right? It's a reducing agent, so I need to quench afterwards. Someone was trying to come ask me if there's a hard and fast rule, but there's really not. You have to kind of think about the mechanisms. You have to think about what's happening. You have to think, hey, like, an LAH reaction, and I kind of skipped a step here, right? It would look like this. It'd have a negative charge. So I'd need something to get rid of that negative charge. I'd need to quench at the end, right? So that's why I would do something like this. Because that helps me quench at the end, right? So understanding the mechanisms helps me think about like, oh, like I need to, when do I add acid? Well, I add acid because this is basic, right? This is negatively charged. This is a basic reaction. It's gonna be a negatively charged reaction. I need to quench it at the end. So it makes sense to do this. Whereas here, acidic conditions, I have water already around. I don't need to add anything else.
Can I ask one more question?
Sure.
If you have an acyl chloride, um, and you form a tetrahedral intermediate, say like a nitrogen nucleophile attacks the acyl chloride, and you have
Sure.
to do a proton transfer, would you just like delete the proton from the NH2 whatever that just added in, and then like not do a proton transfer since the chloride would be the leaving group?
Yeah, so you don't really even need to do these reactions in acidic conditions. Usually you're doing acidic conditions so you can make something that's a poor leaving group a better leaving group. Uh, so we can do these in just neutral conditions, and often they are done that way. All right, and then you deprotonate it. And you can see why, right? The proton would be unnecessary. This leaving group is already a good leaving group. If I compare that to up here, we need this acid specifically because OH is not a good leaving group. And so the acid eventually gets to this to make it a better leaving group. So really, the acids are done to catalyze the reaction by making a good leaving group here. That's unnecessary here because we already have a chlorine. So I'll very rarely give you this kind of reaction without an acid or with an acid because it's just not necessary.
Thank you.
Because the acids are used to make the leaving groups better leaving groups, which we already got. Oh, what a good question. What a great question. All right. Sophie asked. All right. Let's say we got, let's say we got this, and you have some sort of acid around. This is a problem because this carbon takes the acid, and now you know, that's just a non-reactive carbon. The question is, we just did a reaction that looked just like this with an acid present. Would this not just take that acid? And it would. And it does all the time. I would actually say 99% of the time it's taking that acid. 99% of the time, this is what's happening and not the carbonyl protonating. But there's a key difference between these two things. One, this can always go backwards. This will never go backwards, right? This is actually the slightly more stable form than this, whereas this is so much more stable than this, right? So this can go backwards. This can't. So what happens is these go back and forth, these go back and forth, these go back and forth. And then the one time this happens out of a million, the one time that happens, this guy goes, it attacks and we kick off water and we end up forming the pretty stable imine. So it's not that this doesn't happen, it's that when this forms, we can always go back, right? This is more acidic than this. Like this is relatively acidic. We can take that proton right back off. This is not acidic at all. I cannot take this hydrogen back off. So using a negative nucleophile matters, right? It's the using a negative nucleophile means that we can't have any sort of acid around because we get locked here. Or here, there's equilibrium here. Um, so Sophie asked, would it be faster if we add the acid first? So that's a good idea, right? So like let's say we did right, this is the question. Like why don't we just do this? And then this can attack. You can do that. The problem is that this can still do this. Like you still kind of can end up with the same thing. Like it doesn't really solve the problem. The acid-based stuff is specifically like acids, like that proton just bounces around. Like it's almost like a lie to say that it's on any one thing. It's kind of just bouncing around, right? So um you still kind of run into the same issue. It doesn't, you can try it. It might be faster, but that proton's not really useful to practically think as being like in any one place. Acid-base reactions are happening so fast and they're being transferred around like nothing, that it doesn't really matter. But this is kind of outside the scope of the test, so. But it's a good question. Any other questions? I feel like I kind of skipped through the synthesis, and I don't want you guys to feel like I skipped through it, but at the end of the day, synthesis, I'll say the focus should be on retrosynthesis, and that's what I've tried to make clear through the quizzes, is that retrosynthesis might seem like a small deal because it's only one reaction out of potentially like 10 or 20, but those are the important reactions. Those are the places that give you the landmarks to work towards, right? You're essentially making one huge synthesis problem into three, four, two, three, four smaller synthesis problems that are a lot easier to do. And so we're going to look at the retrosynthesis. I want you to focus on the retrosynthesis because that's the key of doing synthesis, right? Ask any organic chemist. They'll tell you that retrosynthesis is the most important skill when it comes to planning out chemistry, being able to do retrosynthesis. So, um, if you're still struggling with that, I would say the heart of it is doing retrosynthesis and really understanding what you're doing and why you're doing it. And there's so much practice we have on that through old recitation worksheets and stuff. And then once you have the retrosynthesis down, once you're getting that 100% right, I would go back through the lecture notes and find any place we've done synthesis because I've posted both the retro and the forward and everything from old lecture notes. So anytime you see synthesis in old lecture note, try the retrosynthesis and then try it forward. There's a lot of back practice that is there. And trust me, there's enough that it would be fresh to go back through it and do it again. You're not going to remember all those answers. So um, synthesis is one of those things that just takes a little bit of work, but once it clicks, it makes sense. And I think you guys are doing a pretty good job with it. We added, honestly, the protecting group is the smallest thing. Like if you don't get the protecting group, you could still probably get, 80% on the synthesis, right? If you just never do a protecting group, but it does help. And really what I want it to get you to do is to start thinking about like, hey, are there multiple nucleophiles? Are there multiple electrophiles? Do I have to be careful about this? Um, so I've got a couple more minutes. I can maybe answer one or two more questions, but then I've got to get off and go towards a meeting. So, do you guys have anything else I can talk about or summarize that you guys are worried about for the test?
So these are like the major topics we need to know, like synthesis, carbonyls, carboxylic acid, epoxides. Like, is there anything else?
Yeah, I mean, really, organic chemistry can be kind of broken down into two main ideas. Can you understand the mechanism of how reactions work, right? Can you walk me through how a reaction functions? Then can you understand that well enough and then zoom out and chain together multiple reactions to get to a final product, right? So yeah, the main ideas are of any organic test is going to be, do you know mechanisms and do you know synthesis, right? Do you know how each reaction works on a very minute level? And then can you chain those reactions together? Specifically, we've done a lot of stuff with carbonyls. We've done a lot of stuff. Carbonyls naturally lead themselves to conversations about equilibrium, epoxides, carboxylic acids, and then using those in synthesis. Yeah, so that's the test, right? That's all I could ask you is, do you understand the reactions, and then can you use them in a practical way?
Um, can you kind of talk about hard versus soft
Oh, yeah.
nucleophiles again?
Yeah,
Just very lightly.
yeah, that was in your practice test, wasn't it? So this is a recurring idea, right? If there's a spectrum between something being a perfect base and something being a perfect nucleophile, um, we would say something is like this is a spectrum, right? A base and a nucleophile are similar in that they're both electron donors, but what they give their electrons to is different, right? So base, this usually takes protons, whereas nucleophiles attack electrophiles. So it just turns out that things that are softer tend to be more nucleophilic, and things that are harder tend to be more basic. So the reason we use this soft versus hard is because it's kind of a convenient way to see a trend that we've noticed. So if charge is spread out, so I think we could agree that this is going to be an electron donor of some kind, right? But when compared to something like this, notice that there's resonance that spreads this charge out over multiple atoms, right? So that idea that this charge is spread, it's delocalized, this gives it a softer vibe, right? This is what we describe as harder because this charge is only on this oxygen. This charge has been spread out. It's like foam. It's aerated. It's, you know, got space in it, right? And so I would say this tends to be a softer nucleophile because that charge is spread out compared to oxygen, right? Similarly, like something like sulfur is much bigger than something like oxygen. So that's another way I can kind of spread out the charge, right? These things are more nucleophilic than they are basic, right? Whereas this alkoxide, this is fairly basic, right? A secondary alkyl halide and you're getting elimination, right? Um, Another way you can see it is like sodium hydride versus lithium aluminum hydride, right? They're both H minuses, but the positive charge, what they're bound to, helps stabilize that negative charge. It helps spread it out. And so you see LAH acting more of a soft nucleophile, which is why it tends to be more nucleophilic, where sodium hydride is a harder nucleophile, right? It's just a little sodium and a little hydrogen, right? And that those charges aren't spread out very much. So this kind of helps us explain and predict that sodium hydride is only going to ever act as a base, where lithium aluminum hydride often acts as a nucleophile. But again, these are spectrums, right? LAH can still take a proton. That certainly happens. So it's not fully nucleophilic, right? But it's more nucleophilic than sodium hydride, which is essentially not nucleophilic at all. Um, Likewise, alkyl lithiums are harder nucleophiles because lithium is small little charge, or something like that is softer, spread out. Charges spread across that big old copper. So it's kind of a trend that we see where things with delocalized charge, with spread out charges, tend to be more nucleophilic. And so we kind of gave it a name to be softer, which all that means is the charge is spread out. Here, the charge is more localized, right? We get small counterions or the charges on this little oxygen that's not spread out. These things tend to be harder. And if I'm honest, this oxygen is kind of more like, right? It's a spectrum. Things aren't perfectly hard or soft, but it's hard compared to this, but it's softer than, say, sodium hydride. But it's within a spectrum. Does that make
Thank
sense?
you.
Yeah.
Yeah.
And I mean, likewise, LAH is probably a little bit harder, right? Just because it's still a H minus. So it's all kind of in this spectrum of things. Softer things have more spread out charges, and we see that they tend to act more nucleophilic and less basic. All right. So if anybody doesn't have a quick question I can answer, I'm going to hop off, but thank you guys for joining me. And I will stop the recording.